This is the Unit 5 video, and this is page 3 and 4. So starting with number 17, it says identify the zeros of the function shown in the graph. So zeros will be your x-intercepts. So I have one. First I'm going to start by circling. I have one here, here, and here. Okay, so right here, so I have x equals -1. Notice that this right here is a double root. So we have 0 twice because it's a double root, and then we have right here, which is also a double root, so we have 1 twice. So those are the zeros. Okay, moving on to the next one, identify the zeros again of the function. So I have here, and here, and here. So then I just list, because if I want the zeros, it's x equals -2. Notice that this right here is actually a triple root. Okay, a triple root has this shape right here. A double root is the one that bumps right up against the x-axis. So because I have a triple root at 1, I'm going to list 1 3 times. And then right here, which is 4. Okay. All right, let's keep going. Identify the x-intercepts of the function. So x-intercepts of the function. So if I have something that's already factored, I'm going to put each of these equal to 0, and those are going to give me the x-intercepts. So x equals 0, so that's this one. I have 5x minus 4 equals 0. X plus 1 equals 0. Right down here, x minus 3 equals 0, and x plus 17 equals 0. So then I'm going to solve. So I have x equals 0, that's already solved, so I have 0. Here, I have to plus 4 on both sides. So that gives me 5x equals 4, divide by 5. So x equals 4 over 5. So 4 over 5 is going to be one of my zeros. Minus 1 on both sides for this one. X equals -1. So I have a zero of x-intercept is -1. Plus 3. X equals 3. 3. And then minus 17. So x equals -17. So my zeros are x equals 0, 4 over 5, -1, 3, and -17. And x-intercepts, we're going to list them as ordered pairs, so then we know that the y value at the x-intercept is 0, so I have 0, 0. I have 4 over 5, 0. I have -1, 0. I have 3, 0. And then I have -17, 0. Those are all my x-intercepts. Okay, the next one says identify all the double roots in the below graph. Okay, remember the double root is the one that comes and bumps right against the axis. That's a double root. So I have a double root right there, which that double root is going to be at x equals 0. And then I have a double root right here, which x equals 2. So those are both double roots. Notice again that it's the parabola that bumps against the x-axis is going to be the double root. And then if I have one that looks kind of like a cubic function, so it's going kind of flattening out here on the x-axis and then going down, that's what we call a triple root. Okay, so that's the difference between triple and double. All right, moving on. Okay, so for these, you're probably going to need an extra piece of paper. But the first one says write the function with the given zeros. Write it in factored form and then write it in standard form. So you're going to need a little bit of room to do this. So factored form, if this is the zeros, okay, then the factors are x plus 3, x plus 3. Okay, so x plus 3, which is the same thing as writing x plus 3 squared. Now in order to factor that, I I'm sorry, in order to write that in standard form, because those are the factors, you're actually going to have to multiply these by using FOIL or the box method. So the first one I will do FOIL with. So you're going to distribute the x here. So x times x is x squared. X times 3 is 3x. And then here, 3 times x is 3x. 3 times 3 is 9. I can combine my two like terms. X squared equals 6x. Oh, sorry, x squared plus 6x plus 9. So that would be standard form. Again, x squared plus 6x plus 9. So you actually have to multiply them together to get to standard form. So if you have the zeros, you can go to the factored form. Notice it's the opposite sign, and then to standard form. So let's do the next one. The next one has 3. Okay, so I have x minus 7 times x plus 2i times x minus 2i. Okay, so I want to take a look at this because these look funny because these are actually not the factors, okay, even though we're kind of following the same pattern. So what you want to do, if you don't recognize what the factors are, you could multiply these two together. Okay, so I have x plus 2i times x minus 2i. Okay, so I'm going to do the same thing as I did in that first one. Now we're going to, that x plus 7, we're going to leave that alone for right now. So x times x is x squared. X times negative 2i is negative 2ix plus 2ix. And then 2i times negative 2i is minus 4i squared. Okay, notice here these two middle terms cancel out because I have minus 2ix plus 2ix, so they go away. So I have x squared minus 4i squared. Okay, well, if you remember from 2 units ago, I squared equals negative 1. If you don't remember that, you could put that into the calculator. So remember your I button is right above the period, so second period to the power of 2 is negative 1. Okay, so then I have x squared minus 4 times negative 1. Well, negative 4 times negative 1 is positive 1, so x squared plus 4. So that's your factor. So instead of writing it like this, you're actually going to need to write it as x squared plus 4. Okay, so then we also still have our x minus 7. So we're going to take that and put that here, x minus 7, because we need to multiply these two together, because in standard form, you've got to multiply the factors back together. So we're going to multiply x squared times x is x to the third. X squared times minus 7x is minus 7x squared. 4 times x is plus 4x. And 4 times negative 7 is 28. Oh, minus 28. Okay, look to see if there's anything you can combine. There's not. Make sure that these standard order means that it's in descending order. 3, 2, 1, no exponent. So that's my standard form. All right, let's take a look at the next one. So I have x, it's positive, so minus 1, x plus 4, x minus 4. All right, so right here, I recognize that as the difference of perfect squares. So I know that that should be written as x minus 1 times x squared minus 16. If you didn't see that right away, then you can always multiply those two together, x plus 4, x minus 4, just like we did up here. But I'm going to continue with this. So I have x minus 1 times x squared minus 16. Multiply x to the third minus 16x minus x squared plus 16. remember that in standard form, that means that they have to be in order. So I have x to the third minus x squared minus 16x plus 16. Now they're in order. We're in standard form. So I have x to the third minus x squared minus 16x plus 16. That's your final answer. Just to clarify here, your factors are x minus 1, x plus 4, x minus 4. I just simplified it here before I multiplied, so the x squared minus 16 made it easier for me to multiply the other two together. Okay, so my factors for the last one, so I have x minus 7, and then notice that the pattern here is to say x minus or plus whatever the number is. Well, x minus 0 or x plus 0 is just x. Okay, well, if that's the case, then I know I have an x, and then I have another x. So x minus 7 times x times x. It's pretty simple to do. So on the outside, I know x times x is x squared. I'm going to write it over here on the front. So x squared times x minus 7. Distribute that in. X squared times x is x to the third. X squared times negative 7 is minus 7x squared. So that's your standard form. They're in order. And that's it. All right, let's take a look at another one. It says graph each on your graphing calculator and fill in the number of solutions and each type. Okay, so the first one, f of x equals x to the third minus x squared plus 4x minus 4. So it wants to know the degree. Okay, well, the degree is also going to be the same number of complex solutions. Now, in order to find out if they're real, double roots, or imaginary, that's when we need to put that into the calculator. Let's go ahead and get your calculator out and plug that into the calculator. Okay, so we know we need 3 solutions. So we see that there's one solution that is a real solution, okay, where it's going through the x-axis. So I have one real solution. There are no double roots, which means I need a total of 3, which means I have to have 2 imaginary, because the imaginary plus the real should add up to the total complex numbers. Okay, go ahead and put the next one in. Notice that we should have a degree of 4, which means I have 4 complex solutions. Now you need to put it into your calculator to decide if they're real or imaginary. Okay, so I have 2 very distinct, and if you want to zoom out, you could zoom out to try to get a better picture. And you can see there's just one, it looks like a quadratic, which means I've got 2 real. So I have 2 very distinct places where it crosses the x-axis, which means I have to have 2 imaginary. All right, let's go to the next one. I have f of x equals 8x squared minus 16, so I have a degree of 2, which means I have 2 complex solutions. You just have to decide which are imaginary and which are real. Go back to zoom 6 so I can see the graph. So I see that I have a 0 here, 0 here, which are the same as roots, which means I have 2 real solutions. There's no double roots, and there are no imaginary. All right, and then the last one. Okay, my degree is 4, which means I have 4 complex solutions. This looks like a quadratic, so I have a real solution here and a real solution here, which means I have 2 real. There's no double roots, and that means I have to have 2 imaginary, because remember, the imaginary plus the real have to add up to your complex solutions. Okay, number 29 says to determine the number of real solutions and non-real solutions. So very similar to what we were doing a second ago. So you're going to have to put this into the calculator. Okay, notice the degree of this is 3, so I have to have 3 total. Whether they're real or non-real, there has to be 3 total because the complex solutions are going to be a total of the degree, which is 3. So I'm going to hit graph. Okay, so I see that it's going through the x-axis once, which means that I need a total of 3, so there has to be 2 non-real or imaginary solutions. Okay, the next says, using the given factors, sketch the graph. Use your calculator to help. Make sure that you emphasize the zeros. Okay, so the first connection I want you to make is that if we're looking at this, these are already in factored form. I know that I have a 0 at x equals 0, x equals 2, x equals negative 3. So you should be able to start there, that I have a 0 here, x equals 2, and that x equals negative 3. Okay, so now you can use your calculator and put it into y equals so that you can sketch the rest of the graph. So x, please make sure you enter it exactly how you see it with the parentheses. Okay, so we're going to graph. Note if I have a 0 at negative 3, 0 and 2, just like we predicted. Okay, and this does say sketch. You can go into your table and find some exact points. Make sure you're looking for points that actually fit onto the graph. So 1, negative 4 would work. And hopefully your graph looks way better than mine does. Okay. All right, so you're going to go through and you're going to do that for all of these. So this one, I have x equals 0. This one, because this is squared, that means I have a double root. So that's going to be x equals negative 3 and x equals negative 3. And then x equals negative 5. So you can start there. Negative 3 and positive 5. So go ahead and put it into the calculator, see what it looks like. Again, it needs to go exactly how it appears. Okay. So we said that we have a 0 at x at negative 5. We have a 0 at a double root at negative 3. And then we have x equals 0. So this actually plot on the wrong side, right? So x equals negative 5. That's over here. Not go there. So because we said x equals negative 5. So it's kind of easy to see this part. So I'm coming down here. And remember, it's bumping up to the graph because it's actually a double root there. And then this part's hard to see. So if you zoom box, because it was hard to see that there was actually going through 0. So I just want to look through. So if you could do zoom box, enter, and then create a box there where x equals 0, so I can be sure that that's where the graph is going, because that's what we predicted. And C, you can see that that part of the function is actually going through 0, 0. Zoom 6 takes you back. So it's going down, and then up, very sharply up like that. All right. Okay, so last one, we have x plus 2 squared, so that's a double 0. So I have x equals negative 2, x equals negative 2. And then I have another double 0, x equals 1, x equals 1. And then I have x minus 3, which is x equals 3. So I have a double 0 at negative 2. I have a double 0 at 1. And I have a single at 3. All right, go ahead and put that into your calculator and sketch it. All right, when we put it in, we see that it comes up, bumps up against the graph, like we said, because that was going to be a double 0. Down, up again, bumps to the graph because it's a double 0. Down, and then through, positive 3. There's your graph. Again, you can go to the table if you want to get some more exact values, if you want to maybe make that look a little prettier. All right, the next one. Which is the correct factored form of the function? Okay, well, factored, so we've been kind of flipping back and forth between zeros, x-intercepts, what's the factored form, standard form. So first of all, this picture is going to give you what the zeros are. So I have a 0 of x equals -1, x equals +2. Well, so if those are the zeros, the factors are going to be x plus 1, x minus 2. So those are our factors. Now notice also that this is turned down. So a factor of x plus 1, x minus 2. And I'm facing down, so I know that in front it has to be negative in order for that parabola to face down. So let's take a look. X plus 1, x minus 2. I have a negative in front because it's facing down. You can always put this into the calculator and double check to make sure that it's right. Negative x plus 1, x minus 2, 6. And we can see that that matches. All right, last one. Are there any double zeros in the graph? If so, where? Okay. So take a look. Remember what we talked about double zeros and how they look, how they bump up against the axis. Okay, here I see this is a single root because it's going through, single root, single root. So I do not see any double, which means the answer is no. Remember, this is the one that looks like a double. It just hits. It doesn't go through, it actually just hits and then comes back down. It's a turning point. All right, and that's it for page 3 and 4.